So we said that mu, which is the frequency, equals C over lambda. And this is usually represented, the unit is hertz or second minus 1. And that this is the speed of light in vacuum. Thank you. Okay, so on Friday we were talking about the relationship between frequency, the electromagnetic spectrum, how to calculate the energy of light. So we learned that mu, which is the frequency, hertz second minus 1, equals the speed of light, which is usually given to you as a constant in meter per second, over lambda, which usually in meter, you're going to plug it in this in meters, and it is the wavelength. Then we talked about the energy, that energy equals h mu, that means equal to the frequency, that means energy and the frequency are proportional. And we said that the energy equals also hc over lambda. So the energy is inversely proportional to lambda. And we talked about the electromagnetic spectrum, and we learned which one has the highest energy, which is the lowest energy. We said that the gamma radiation is the highest in energy, that means the shortest in wavelength, and that the radio frequency is the longest in wavelength, yet is the lowest in energy. And we zoomed into the visible spectrum, to the visible region, which is the only region that we can see, and we learned that the red is the one with the lowest energy and the violet is the one with the highest energy. And just a reminder that the visible is here, below it, above it there is the UV, and below it is the IR. This is lower energy, and this is why it is called infrared, below red, because red is here, violet color is here. This is why we call it ultraviolet, above the violet. And this is definitely higher in energy than the visible region. Okay? Now, let's do an eye clicker on this subject so that we can move to another one. I'm going to stop it at 1 minute. Okay, so I'm stopping it right here to check what you have. So I have E as the most popular answer, and E is the right answer. So the way that you have, if you know the acronym ROI, TVIV, V being the highest in energy. Remember, energy and frequency are proportional. So the higher the frequency, the higher the energy, or the higher the energy, the higher the frequency. So As you can see that the orange is definitely less in frequency than the yellow, than the blue, than the violet. So E is the right answer. Any of the other answers, there is a mistake right there. Either it's a switch, the frequency is a switch, or the whole series is wrong. So E is the right answer for this one. Now let's do more. And I'm gonna stop it at 150. So what is the frequency of light that has 396.15 nanometer as wavelength? And by the way, the equations for wavelengths, for the energy, you're gonna be given those in the exam. The information page, the first page of exam 2 is already on Moodle. Under practice exams.
Oh, I thought that was an answer. Oh, look at that. What was what? A? No, we have to turn the 14th actually.
Okay.
Because
So I'm going to stop it right here and check. And check what did you think about
This isn't on the list exam.
Oh, I have almost everything there. The percentage is not that high. So let's see what went wrong. So A is the right answer. But let's see where. So first of all, it's asking me mainly it is a relationship between frequency and wavelength. Okay? So the frequency equals C over lambda, where C is the speed of light, the wavelength is lambda. In this case, I have lambda, I have the speed, I want to calculate the frequency. So frequency equals C. C is given to me right there. It's 2.998 times 10 to the 8 meter second minus 1. Right? So the lambda, the only thing that went wrong if you answer B or C is you either forget to convert from nanometer to meter, or you did the conversion in a wrong way. Okay? So first of all, I have it in nanometer. If I put it in nanometer, I can't cancel. I can't be talking about meter and nanometers, so I have to convert from nanometer to meter. And we know that the conversion factor, so 369.15 nanometer. I know that the conversion factor is 10 to the minus 9 meter over 1 nanometer. Now the nanometer cancels the nanometer, and I have it in meter, and A is the right answer. Okay? So the only thing that can go wrong in here is not converting right. And this is why in the first chapter I kept saying, please learn the conversions, otherwise you're gonna be in trouble when we get to chapter 5 and 6. Okay, let's do one more. So another conversion that it's a new conversion is 1 kilohertz. We deal with it the same as going from kilogram to gram, from kilohertz to hertz. It's 10 to the 3 hertz. So in other words, the conversion factor is 10 to the 3. If we're going from the big one to the small one, it's positive 10 to the power plus 3. If it is from the small one to the big one, it's minus. And 1 megahertz, and this is mega, not milli. Megahertz, this is why we write it as big one, equal 10 to the 6 hertz. So you need to know those two conversion factors. So let's do an eye curve on this one. So your favorite music station has a frequency at 99.1 megahertz. What is the wavelength of your favorite station, radio station? I'm gonna stop it at 1.
I didn't even know you. Yeah, I know.
Okay, check what you think. So I have B as 78%. B is the right answer. So again, it's a frequency and wavelength. The frequency equals C over lambda. In this case, we need to calculate lambda, so lambda equals C over the frequency. Again, the only thing that can go wrong is if you don't do the conversion, or you do the conversion in the wrong way. So I have 2998 times 10 to the 8, this is the speed of light, it's in meter sec minus 1, over the frequency, it is 99.1 megahertz, and I know that the conversion factor is 10 to the 6. I'm going from the big unit to the small unit. And lambda will be equal to 3 meters. Okay. So let's do more on the same concept. So what is the energy of the electromagnetic radiation with that with this wavelength? And I'm going to stop it at 150. Send your answer if you didn't yet. Okay. So I'll stop it right here and check what you think. And I have 65% for BB is the right answer. So the energy equals hc over lambda. Almost everything is given to you. The only thing is you have to make sure that all of them are in a compatible unit. So the H, which is a blank constant, is 6 times 10 to the minus 3 joule second multiplied by 29, which is the speed of light, and second minus 1 over lambda, which is 396.15 nanometer, now converted to meter. And the energy would be 5 times 10 to the minus 19. So now we learned how if I have a wavelength, I can calculate the energy. If I have a frequency, I can change it to lambda. If I have lambda, I can know what is the frequency. So this is the first lecture, which is learning the electromagnetic radiation. Now the main idea of all of this is from this to learn the structure of the atom, which we're gonna do right now. Everybody has a film, the thin film there. Did everybody get a transparent film in there? So what we're gonna do right now is okay. So I'm gonna turn off the lights so that you can see it better. So what you need to do is the following, guys. As Jake is, these are lamps with different gases, and what Jake is gonna do is I'm gonna apply very, very high voltage to those lamps. As he is applying the voltage, you need to take your film, the film that you have, and move it right and left, and check what you're gonna see. Go ahead. So we're gonna start with the first lamp. Anybody seen something? No, just move it until you see something there. Kind, you should see 3 lines of light. Anybody seen that? Raise your hand if you do. Very good.
Hold it vertically.
For this side, we're gonna come to this side.
I see nothing.
Okay?
It's wet. I turn it that way.
Move close to your face. Leave it on that close.
So go to the other.
The
Really?
rainbow. We'll do the rainbow. No, I didn't.
Okay? Everybody seen 3 lines or 2 lines? What colors are the lines for the first lamp? Something like this? No, when you have the film, not when you're looking directly to it. Green, yellow, and orange. That's right. Let's go to the other lamp. If you're not seeing anything, you have either to put it right or left and look with an angle. And you should see 3 sharp lines or 2 sharp lines. Yes.
We're too far away.
Yeah, on this. Okay? On the screen, on the film, on that film, you would see 3 distinct lines. Okay? Okay? On the film, not in general. You have to put the film, look to the right, to the left of the film, put it that way until you see 3 distinct lines. Go to the other one. Okay. And we're going to turn it off for the moment to go to the other side of the class. Okay. Okay, now this part of the class, let's put it in here. I just have to unplug my computer.
Make some sick glasses with these.
Okay, so what you have to do is to take this pencil, and Jake is applying the very high voltage. You look to the film, and you should see 4 or 3 distinct lines. Are you seeing that? Take it this side. You go this side. Can you see now? Look to the film. No? Yes? Yeah. Take it to the right and look to the film. Move it from one lamp to the other. Don't apply high voltage for a long time. Okay, to the other one. Everybody saw it. Raise your hand if you saw the 3 lines. Raise your hand. So if you don't see it, that means you're looking on the wrong place. You have to look on the film, put the film right, and look at it or left to you. And you should see very sharp 3 lines or 2 lines. Okay, so let's stop it right there. And let's see, what does that mean? So, what we just did, we have 5 different elements: neon, hydrogen, mercury, and we applied very, very high voltage to those. And as we're looking through the film, we saw different, or some of you saw, some very distinct lines. They saw, for example, red, orange, green, 3 lines very apart from each other. And that was kind of a mystery for a long time. Why do atoms do that? And how to interpret that? And what does that mean? And that was done by Bohr, Neil Bohr's, and then later on by Rydberg. And this is what we're gonna learn. So first of all, excited atoms emitted light of only certain wavelengths. We didn't see the whole spectrum. We didn't see a rainbow. For example, some of you saw only red, orange, and green. They didn't see the violet. They didn't, especially through the film. I'm not talking about the color of the of the light itself. So, and that was okay. What's going on? Why do we have a light, a certain wavelengths of the light, not the whole rainbow? And is there any other light that we couldn't see because we can only see visible light? So, the idea behind what we just saw is that we have usually the electron, and I have to stop in here and tell you something, that today we're gonna learn the Neil Bohr model of the atom. Later on Wednesday, I'm gonna say, you know what, that model that we're talking about right now is not accurate. And we're gonna learn about the Schrödinger model or the quantum theory. How the quantum theory that usually we use nowadays think about the atom structure. For the moment, we're using classical physics to understand the atom, which is light and the interaction of light. Later on, I'm gonna say, oh no, there is another theory, and we're gonna talk about that later on. So, according to Neil Bohr, those lights are coming. So when we're applying the voltage, the electron in an energy level around the nucleus gonna do a transition, gonna go from one level to the other. Okay, why? Because it is excited, because we put a high voltage, and we call this a process that the atom is absorbing energy. Then after that, when we leave, or after a while, those electrons goes back from higher level to lower level. They transit from higher level to lower level, and by going to the back to the lower level, they emit light, which is what we saw right now, which is in the form of package of energy, which is the light, which we call the light. So when we excite any atom and it gives us light, the light that we saw, the wavelengths of that light corresponds, we can calculate from it how much is the energy, and that's the difference between 2 energy levels inside the atom. Okay? So again, I'm going to repeat that. So the light that we see, the wavelengths, let's say the red, if we saw red. So if we calculate the energy of that red light, that implies that red light corresponds to the difference in energy level between inside the atom. It's due to the transition from one level to the other. Okay? Now, the way that electron transit from one level to the other It is quantized, so it does it in form of integers. It's the same way as when I go up this stair. I go step 1, step 2. There is no half step. I can't stay in a half step for long. I'll just go back to the step 1. And this is what happens also for the energy in the atom. It is quantized. It goes from n equal 1, n equal 2, n equal 3. There is no half step. There is no 2.5. There is no 3.5. And there is no, for example, 3.25 something. And this is why it is quantized, and this is why we don't see the whole rainbow when those atoms emit light. We see only certain wavelengths of light from there. So let's see what's more. So again, let's look at the molecular, at the atomic level. When first the atoms, this is a hydrogen atom, okay? So the hydrogen atom, which is one of these labs, was in the ground state. That means it's not excited. Soon after, we applied the voltage. We put that Tesla coil in there and excited the atom. The electronic transit did an energy transit or electronic transition from the lower level to a higher level. We call this a process when the electron moves from or transit from a lower energy level to a higher energy level, absorption. So from now on, when I say absorption, that I mean, at least in this chapter, absorption means the electron transition from a lower energy level to a higher energy level. So when it can be from n equal 1 to n equal 2. If the electron is in n equal 2, it can be from n equal 2 to n equal 3. It's not definitely from n equal 1. It depends on the atom and in which shell are the outmost electrons, are the valence electron, which we're going to talk about on next chapter. Now, when the electrons goes back from the higher energy level to the lower energy level, we call that emission, and it yields an emission of light. In this one, it absorbs energy, it's called absorption. In this case, when it goes from the higher energy levels to the lower energy levels, that's emission. So that's the definition of absorption and emission. Absorption is when the electron transits from a lower energy level to a higher energy level, and the emission is when the electron transits from a higher energy level to a lower energy level. Now let's start with the hydrogen, which is the first lamp that we saw, and some of you saw the red, green, and the blue color in there. Okay? Those red, green, and the blue colors, the two blue colors in there, goes back to what we call the Balmer series. And it's the series, as you can see, the blue one is when the electrons comes back from n equals 6 to n equal 2. And the other one, which is the slight blue, is when it goes back from n equal 5 to n equal 2. Now the green color is when it transits back from n4 to n2, and the red one is when it transits back from 3 to 2. You don't need to know which color corresponds. You don't need to know the numbers. You don't need to know if it is transiting from where to where. This is just we're explaining the phenomena that we just saw in here. Then we're gonna learn by an equation how to calculate those energy levels. How to calculate how much is the difference between these energy levels. So all of these are in the visible region. And as you can see, there is the ultraviolet region is right there that we can't see by our eyes. It was there, we couldn't see it, we can't see UV. Now I'll go back to the visible region and comment on one thing. As you can see that the difference in energy in here is the smallest compared to this one, while the wavelength is the longest. Can everybody see that? The difference in energy between this level and that level is much smaller than this level and this level. And that corresponded to the longest wavelengths. Why? Because energy and wavelengths are inversely proportional. And this is one of the hardest concepts, is just to make your mind think that the shortest the wavelength, that means that's the highest the energy. It corresponds to the highest energy difference between the energy levels. So all of these are what some of them we saw them, some the others we couldn't. Now we're gonna learn how to calculate the energy level, how much is the energy for each one of these, and how to calculate how much is the energy when the electron transits from a certain level to the other. So the conclusion of what we just said, that the lines that we saw indicate the electron can only make electronic transition between allowed energy levels. The color of the light can be used to calculate the energy, which we just saw a minute ago by using Planck's law, which is E equal hc over lambda. This is Planck's law. So how to calculate the energy? The energy of each level is given, so for n equal 1, for n equal 2, for n equal 3, the energy equal minus RHC. C, R is the Rydberg constant, H is Planck's constant, and C is the speed of light over n squared. Over n squared, where n is the level, the energy level that we're talking about. Okay? So n is the quantum level or the energy level that the atom is in or the electron is in. Now, as you can see that the sign is minus. And this minus represents, it is negative because it's attraction. It's a potential of attraction. What does that mean? So if I say energy level 1 equal minus 2.5 joule, what does that mean? That means that the electron is attracted to the protons in the nucleus by 2 joules. But since it is an attraction force, I have to put a minus there. So the minus sign there represents that it is attraction force, not repulsion. That there isn't repulsion between the electrons and the protons inside the nucleus. So the E gonna be always negative in this case. The energy levels, each energy level energy is minus because it is attraction force. Okay? So what does that tell you? As the energy, as n increases, as we go from n equal 1 to n2 to n3, as n increases, what happens to the energy? Decreases. So as n is increasing, the energy is decreasing. Does that make sense? As the electrons are far away from the nucleus, the attraction force to the protons is decreasing, is less as we go away from the nucleus. And that makes sense because the nucleus has the positive charge, which are the proton, and the electrons are more and more far away from the nucleus. The attraction between it and the nucleus is less. So this is the equation that we're going to use to calculate the energy for each level inside the atom. And this is for the hydrogen atom. This model is for the hydrogen atom. Now, this shows you the levels that n equal 1, n equal 2, n equal 3, n equal 4. As you can see that the energy difference between n equal 1 and n equal 2 is different than n equal 2 and n equal 3, than that between n equal 3 and n equal 4. And the reason behind it, as you go far away from in the level, the difference in energy level decreases. And I have to stop right here and say that every semester I ask exactly the same question and 50% of the class get it wrong. And the reason, the question usually, as you go with the energy levels, is the difference between energy level equal? No, it's not equal. It's get less and less as you go away, far away from the nucleus. Okay? Now, n equal infinity, when the electron transits from a lower energy level to n equal infinity, that implies the electron is no more under the attraction force of the nucleus. In other words, this atom lost the electron. The same as when sodium loses one electron and it is sodium plus, it is due to a transition of the electron from in one of the energy levels to an infinity. That means to outside the atom. And we call this ionization energy if it is in the gas phase. Only if it is in the gas phase, we call this ionization energy. So as N increases, the levels get closer together. Now, if I have a transition from N equal 1, let's say, to N equal 3, this is the equation, and you will be given this equation in the exam, but you need to know how to use it. So this is, let's say, I have an electron that transits from N equal 1 to N equal 3. The delta E, which is the difference between the two energy, equal minus RHC 1 over N squared final minus N squared initial. Okay? And what does that mean? N squared final in this case equals 3. That means 1 over 3 squared. And the N initial is where the electron started transiting from, which is 1 in here. Now, if your delta E, if after you calculate delta E, if delta E is positive, that means this is an absorption. If delta E is negative, that is an emission. And in other words, if you have an emission, that means the electron is transiting from a higher energy level to a lower energy level, your delta E is going to be negative. And if the electron is transiting from a lower energy level to a higher energy level, it's going to be positive. Does that make sense? Yeah. No, it's not. No. Is it the same? Okay. If it goes back to 1, yes, but it will be a different sign. If it is plus, it's going to be minus. If it is minus, it's going to be plus. But that's if it goes, sometimes the electron goes back to the same level or to the higher level or lower level. But if it is to the same level, yes, it's the same amount of energy, but negative or positive. Okay, so now, from this difference of energy, we said that delta E, we calculated the delta E in the one before, which is minus RHC 1 N final minus N squared initial. Now, from delta E, we can know the wavelength. That means the light that we're going to see. And delta E, we know that the energy equals hc over lambda. Therefore, the lambda going to be hc over delta E. But in this case, we put absolute E because the difference in delta E between the energy level can be plus or minus. This is why we put it in absolute value. We take the absolute value because there is no wavelength which is negative. There is no minus 3 meter wavelengths or minus 2 nanometer wavelength. In other words, you can, from the energy that you figure out, you can know what wavelengths of light can be emitted. You know the wavelengths, you know the visible region, you can figure out whether it's going to be red, green, blue light that you're going to see from that transition. Does that make sense? So, here is a transition between, we have two arrows in this one, so we excited the molecule or the atom in here, and we see two transitions. I'm going to call this transition A, and this is the transition B. Okay? Which one would have a higher lambda? A or longer lambda? A or B? Think about it. Take a minute and think about it. Okay. So, For this transition, the energy difference delta EA is much bigger than delta EB, right? Than the transition B. And we said that energy and wavelengths are inversely proportional. That means lambda A gonna definitely be shorter than lambda B because it's inversely proportional. And this is what you have to keep in mind all the time, that wavelengths and energy are inversely proportional. The higher the energy, the lower, the shortest is the wavelengths. Okay? Okay, let's see what do we have. Let's do some article about the concept of this concept.
Oh, right. Yeah.
1/5 squared minus 1/2 squared.
Wait. Megan, I'm pretty sure it's on. Because it's negative.
Please send your answer if you did not get it. Yes, B is the right answer. So, first of all, delta E equal minus RHC 1 over n squared minus 1 over n squared. So just to make it easier in use, I did multiply the 3 R times H times C. In the exam, you need to do that. You will be given all of those. So it is minus 2.179 times 10 to the minus 18 over. Now, first of all, I have to determine what is n final and 1 initial. So the electronic transition from n equal to, so this is initial, to n equal 5. That means that's the final. So it is 5 squared minus 1, 2 squared. And then delta E will be equal B, answer B, which is 7, 6 times 10 to the minus 19, 2. Now, I'm not sure how many did it chose. Okay, if you chose C or D, what you did is a calculation mistake, which is the following. You thought it is 1, 5 squared minus 2 squared. This is what you plug in your calculator, and that's wrong. Okay? Don't do that, because most of the time in the exam, this is what most of you would do. Instead of doing 1 over 25 over 1 over quarter, or plugging it right in your calculator, you would do something like that. And this does not equal 1, 5 minus over 2 squared. Those two are not equal. So make sure you're using the right you're doing the calculation right, even if you know how to plug in the numbers in the equation. Let's do one more. Yeah. It's supposed to be, okay, I'm gonna stop it as I click it. I'm gonna totally stop it, because it's the same question. It's supposed to be from the first to the second, and the idea behind it that it's gonna be exactly the same energy, but it's gonna be instead of minus plus. So this is the idea of the question, to get it the other way around. So the electron in the first question transit from 2 to 5. In this case, it's gonna go from 5 to 2. Okay, so it's gonna be opposite. Direct, the same amount, but opposite in sign. Okay, let's do this one in here. So which of the following statements is right about the classification of the above electronic transition? I'm going to stop it at 1 minute. Okay, so we're gonna finish the cycling here. As you're leaving, I want you to put the film back into this one or this one. Not right now, until we finish the eye clicker. I would have 2 places to put it, or let's put it in 3 places. This one, in here, and there. Okay? So I'm gonna stop it right here and check what you think of. So I have B as 95%, that's great. So, okay, I'm not done yet. I'm not done yet. So everybody is staying and listen. Okay? So, for A is absorption. No, it's not absorption because it's emission. It's going from the higher energy level to the lower. B is absorption, yes. So the first A is definitely wrong. Let's check B. A is emission, that's right, that's an emission. B is absorption, that's right. C is absorption, that's right, it's going from lower to higher energy level. And D is ionization, yes, because it's going from an lower energy level to an infinite. Okay? See you tomorrow, see you Wednesday. And please put the film back.